All right, let's go over our review for units 9 and 10. So there's the chi-squared problems. Those are the categorical ones, the ones that are proportions. And then the linear regressions, which are the tests or the inferences about slope or the linear relationship between things. So they're mixed in together. So you have to kind of decide between that first and then do the problem. So in this first problem, we had computer printout for a linear regression t-test, and we wanted to find the standard error of the slope. So the issue is that this S right here, that S is the standard deviation for the residuals. So the average amount that the actual Y is from the predicted Y, not the variation in the slopes that happen from sample to sample. So we remember that one of the things we have to do to get the standard deviation of the slope, S of B, if we just have a computer printout, it's a pain in the butt, B over T. So we had to take the B value, the little b, sample slope 9225.16, and divide it by the T score here, 4.18, and that gave me 2206.98. Now, I had gone out more decimals and found that actually if I didn't round, it gave 2208, which is still closest to C. But the answer C came from rounding to 2 significant digits. Okay, next, we have been given a function here, a prediction equation, an LSRL, least squares regression line, and the standard deviation of the slope. We are then asked to 95% confidence interval for estimating that slope. So remember that to do that confidence interval when we don't have the individual data, we do that with our sample slope B plus or minus critical value T star, and that is based off of the amount of confidence. So since we are 95% confident and I have 95% in the middle, then I have 0.025 here. And then let's see, we were told 12 students. So the degrees of freedom are n minus 2 because of the two variables in linear regressions. So there we fill that in and we get answer A. Oh, that critical value 2.23 times the standard deviation of the slope, which they gave that to us here. All right, next. Here we have got, which of the following is not true? Those get me for some reason. I have to leave out that. So anytime I see that, I got to make a point to think about that. Okay. So for small degrees of freedom, the chi-squared distribution. Okay. So remember, we're thinking about chi-squared. Remember, those are skewed to the right. Okay, because you only have, because chi-squareds, you only have those positive values. So for small degrees of freedom, they are skewed right. They're actually kind of like more skewed right, the smaller degrees of freedom you have. Notice a little bit of what's happening as we have bigger sample or categories, more degrees of freedom. So look kind of at this picture at what's happening. Let me see if I can zoom in here. So if you think about it, if you have more categories, more degrees of freedom, more discrepancy, you're getting this, your chi-squared number is bigger because you have more categories to have a discrepancy with. So then that's what's making that mode be a little bit farther out. So it's kind of stretching out here to the right as you get, and it's kind of becoming almost more normal. It's never going to reach there, of course, but it's kind of becoming a little bit more unimodal or symmetric as you get larger degrees of freedom. So then that means that as we have the smaller ones, it's quite a bit more skewed. All right. For B, we want to, I mentioned also again how it moves farther to the right, and the curves move farther to the right, not more farther. Okay. So you can see that below. All the area under the curve are positive, or the chi-squareds are positive. And then all the area is 1, so the mean is not 0. Okay, that's the expected value is 0 right here, but obviously you can tell that's not the mean of the values. All right, number 4. Here we have the degrees of freedom. And so as we're reading through this problem, we can see that we have got some categorical data. So that's our chi-squared type stuff. So we have 4 categories of surgical methods and 3 categories for pain levels. So for those multiple variables, we would have independence, chi-squared test of independence, rows minus 1 times categories minus 1, or columns minus 1. And so then that is 3 times 2 in this case, which is 6. All right, next we have number 5. Okay, so let's talk a little bit about this one here, because I really want to make sure that you understand what this is doing for us. So that is the ratio that the geneticist claims. So of course our null hypothesis saying that the flies are distributed as the geneticist claims. But so this right here is going to be used in giving us our expected counts out of a sample of 2,000. So we can see here that I would tally up these parts. So 2 plus 3 plus 5 plus 8, that's 18 parts. So then for the first category of flies, I expect there to be 2/18 of the 2,000 are expected to be in that category. And then for the next one, 3/18 of that category, of the 2,000 in that category. Then 5/18 of that 2,000 in that one, and 8/18 of 2,000 will be in the last category. Of course, our observed values were in list 1. So with these claimed percentages, that's a chi-squared goodness of fit. So I went and I ran that with a very low p-value. So I have evidence to reject that geneticist's claim. Okay, so here, the computer output for the regression S is the estimator of sigma. And yes, that is true. S is an estimation of this population standard deviation. Okay, and for our standard deviation, that S there is our standard deviation of the residuals. And now look at this next one. This kind of threw in something that you had not really seen, so I kind of tried to give you some background here. So the t-test statistic for the null hypothesis of the slope is 0 has the same value as the t-test statistic, the null hypothesis rho, that's a lowercase rho, equals 0. So I gave you a hint here because we hadn't talked about this. FYI, the null hypothesis rho equals 0 is the test for the y-intercept, which we've kind of like always ignored. Remember how I've said, hey, look at that computer output. Remember how we don't need anything about the y-intercept except for the y-intercept itself? Okay, so with that, I have kind of, I've kind of left that out there. But if you were to run a test for the y-intercept, okay, then this would be the t-score for that test of comparing the y-intercept to 0. So that t-score is way out there. So there's ain't no way that p-value, that y-intercept is going to be 0 in this case. But don't worry about that. All you need to get from that statement is that the test statistic for the y-intercept is not the same as the test statistic for the slope. That's what the purpose of that statement was. All right, so just being aware. I've not really seen a lot of problems on that, but being aware of what all that stuff is a good thing. So next, the t-test for slope of the regression line is always two-sided, not equal to 0. No, because we can test for if there's just a positive or a negative slope. We could test for the slope being greater than 0 or the slope being less than 0. Okay, so there are those first 6 problems, and the end of this video, you'll get numbers 7 through 12 in the next one.